Hi audience and student. In the last lecture, we went through the details about current loop design of current mode control for buck converter. So now it's time to discuss the voltage loop design for PWM converter. So I'm using buck converter as an easy example, but however, later on, we'll extend this design procedure, almost same procedure, to the boost converter and buck boost converter later. Okay, so let me use buck converter for the simple example. So first one is this. The first concept is control to output transfer function with current loop closed. This is very important. We identify similar transfer function in voltage mode control, but here current loop is already closed. So with that condition, we need to evaluate these things. Okay, and the second one is impact of the current loop or benefit of the current loop. Why we are using current loop feedback? What is the advantage of using this compared to not using this, compared to using only voltage loop alone? Okay, there are substantial benefits of using this additional current feedback. Will be summarize this benefits of current loop. Okay, and later on we'll design the best structure of this voltage loop compensation. I already introduced it as the two-pole 1-0 circuit. I'll explain why this structure is the optimal structure for this case. Okay, this structure can be used for all the PWM converters when current mode control is employed. Okay, and finally, design procedure of the voltage loop will be presented. You will realize that this whole procedure is very simple. Okay? You have two steps. One is current loop design. There is a selection of the just one number. And you have another step, voltage loop design. There is a selection of only two additional numbers. So you should select three numbers. Okay? For the voltage mode control, maybe you need to select 5 or something like that. Okay, so this is much easier than previous one and more systematic and easily understandable if you follow this lecture properly. Okay, so many people think the current mode control is very difficult and complicated. That is not true. Okay, it's even much simpler than voltage mode control if you understand this in proper way and in proper manner. Then everything is simple. Okay. Okay. Let me show this one first. This slide is rather important, and this explains the concept of the control to output transfer function with current loop closed. Okay. First, consider this. Forget about this part, and this is connected, and this is the two-pole 1-0 circuit, and this is connected. This is what? This is complete current mode control. Okay, there is a current loop here, there is a voltage loop here, but this voltage loop is broken, and instead of that, there are something. Okay, this is the auxiliary circuit used to measure transfer function from here to there. Okay, all right. Okay, suppose this is 0. Okay, suppose this is 0. So this VST is on the ground like this. This VST. Then this V-con is some division between this. Okay, division. This VD and divided by some resistor. And this contains the DC component here. Okay, so AC is 0. So there is no AC variable here. So then this becomes, because there is a 4, and assume this is connected somehow, then this is 4, this is 4, then duty ratio should be what? 1/4. So this should be 1.25 Okay, 1.25, and this is TI. This is the V cone. V cone is, I'm not sure this is 1. Assume this is 1. Okay, no. All right. Assume this is 0.25. Maybe I should use some other number, but that's not important. Okay. Then everything is DC. Output is DC. This value should be 4 volt. Okay. And this duty ratio should be, okay, assume this PWM gain is 1, then this should be 0.25. Okay? 0.25. All right. Okay. Okay. So this is the setup. Okay. Now you add the AC perturbations. In perturbation is VST. So there is an AC component here. Okay. Then this is the VS hat. Then this is the duty ratio is this one. Constant times this D hat. D hat. Okay. And this is, oh no, this is not D hat. V cone hat. Hat, and output will be something. Okay. So with this condition, you can measure the ratio between this and this. That is called this control to output transfer function, measured in this fashion. So this GVC is control to output transfer function with current loop closed. Okay. So current loop is closed, but still you can define the transfer function from here. This can be considered as the input to this one, and this output to this part of the circuit. This is called control to output transfer function with current loop closed. Okay, this is notation of VCIS. Input is this one, output is this one. This is very important. Okay, if you know the expression of this or body product of this, then you know how to design this, to obtain the desired loop gain structure with everything included, with current loop embedded with this circuit. Then you can define the loop gain of this whole system. Okay, so designing this part is called voltage loop design, and finding out this transfer function is evaluation of control to output transfer function with current loop closed. So this is a very important transfer function. Control to output transfer function with current loop closed is explained in this manner. And this is the block diagram representation of this circuit diagram. In here, everything is in time domain. So here the DC information and the AC information are all mixed up. Okay, but in next block diagram representation, you are only considering this one. I'm not sure this number. Okay, let me think about this, but it really doesn't matter. Some finite value is fine. Okay, because we have this additional things. If this is the voltage mode control, then this is very easy to find out. Okay, but because of this, I need to know this and the maximum value of this and everything. Okay, so this is simply not the duty ratio of this. Okay, because of this, okay, we went through. Okay, so current sensing waveform is something like this, and I should hit this point. Okay, so I think this is not true. Okay, but it really doesn't matter, right? Okay, so this is the block diagram representation. In the previous voltage mode control, we have this part, and this part. Okay, additional part is here, shown here, right? And you are trying to evaluate the transfer function from here to there with this closed. Okay, then with this one is 0, this one is connected. This is the linear system. So we are talking about the superposition principle. Then we only interested in this path, and this path, this is the inside of this signal path, okay? So then transfer function from here to there is, this is open loop transfer function from here to there, okay, without considering this. So it comes in the numerator, in the denominator, denominator contains 1 plus this loop gain of inner loop, okay? Loop gain means product of 3 functional blocks with negative sign in front, so minus minus cancel. So this is what? This is GVCI expression. TI is this one, this current loop. This is the Mason's gain rule, okay? So you can apply, directly apply Mason's gain rule, or you already know this from the previous study, or you can derive this using the block diagram manipulation. This is the extremely simple. So Mason, I don't know, Mason is right, M-A-S-O-N. Mason, I don't know, Mason's law, okay? And GVD, so this power, no, this one is coming in between, okay? So let me write down this for the future reference. You already know this, or you can easily derive this. This one, okay, GIDS, everything remains same, but this low frequency gain, DC gain is this one. And we have this ESR0, and we have this quadratic term, okay? Okay. Right, this is IL, let me fix this. This is Dury ratio to output transfer function. Dury ratio to inductor current transfer function. This one is Dury ratio to output transfer function. Okay, so it's the same thing. All right. Okay. So we are combining this page and this page here, right? So this is the previous page. This one is the previous page. Okay. The reason I'm showing this is I just like to show one important concept. Okay. So we consider this a new plant. You know what plant is? Okay. Previously, this was the power stage. Okay, for the voltage mode control, but in current mode control, this and this combined all together can be considered as new power stage. Okay, so buck converter power stage combined with this PWM block and this current sensing network is considered new power stage. All right, so this is a new power stage, and we are trying to measure the input to, the control to output transfer function of this new power stage, okay? And this is the small signal model of new power stage. If you understand, you accept the concept of the new power stage, everything is the same as the voltage mode control. Current mode control is embedded inside of this, and if you see this side, this circuit, outside of this part, this looks as one converter, new power stage, okay? So this can be considered as one block, and the disturbance source is here, disturbance source is here, output is here, and this is the input, so you are interested in input to output transfer function. Everything is inside of here, okay? For the voltage mode control, everything remained the same, but this part was missing, okay? Because of we don't have this, right? Okay. So control output transfer function is this one. Okay, this is the reformulation of the previous two slides, and TI is the color loop. Color loop is appearing here. So this color loop is very important. But designing this is extremely trivial. Just the selection of the one point. Okay, so this can be considered as a new concept. Then if you accept this concept, everything becomes very simple, very easy to understand, and very straightforward. All right? Okay. So you are trying to measure this. Okay. So this is the new power stage, and this is the measurement circuit. We are injecting this signal, this AC signal, in addition to this DC signal, but we are only interested in AC signal. Okay. So this is the basic structure of our asymptotic analysis. Okay, this structure is appearing again, and again. Okay, 1 plus something is the generic rule, generic formula for the feedback system. Okay, when you think about your undergrad course, feedback is 1 plus Tn something. Okay, it appears all the time. So we have here. Then we use this asymptotic approximation. When magnitude of the Ti is larger than 1, not much larger than 1, simply larger than 1, then we get rid of this, and otherwise we discard this. Okay, that's the asymptotic analysis, and the Ti is given by this. Okay, then we think about this. We know this. We know this structure. Okay, we know this structure. This is the voltage loop. Okay. This is the structure of the voltage loop, and this is GVD. GVD has double pole here, and the slope is -2, and it has omega ESR, it goes down after that. And this is constant, so just the level, this level is increased or decreased, changed, right? The structure remains the same as this one. We already know structure of this. We already know structure of this. Then we can easily perform asymptotic analysis. Okay? You know the rule of the asymptotic analysis. Okay? Borderline of approximation is this one. This frequency, omega Ci. Okay? After omega Ci, this GVCI is simply follow this one, okay? This one, this G prime, GM prime VD is coming here, right? And below that, you are subtracting this. So you subtract this much from there, this much. Then this length should be the same, okay? So and the slope, you know the slope relationship. This is 0. This is increasing. So you are dividing this. Okay, so this is slope and this +1. So this comes in the denominator. Then it becomes -1. And -1 is coming here. Then after this ESR slope becomes the same. Then it becomes the horizontal line at this point. And it follows this one. Okay, this is the construction of asymptotic analysis. Okay, you know how to do this. Right? Okay. And there is some distance between this and this. They don't have the same line. Okay? It's not. Okay? They're different because of this determined by this length and so on. Okay? How about the phase? Phase is 0 here. This is the horizontal line, and the phase is the slope is -1. Then phase is -90, and in here, phase is 0, it increases to 0. This is -1 slope, phase becomes -90 degree. Okay, so because this part, this portion has -1 slope here, okay? -1 slope here. Okay? Alright. So this is the way of generating this. Why we are trying to find out this? Because we needed to find out the structure of the feedback compensation. Okay? For that, we need to know this structure or transfer function. Structure is better. Knowing the structure is simpler and far better than knowing the equation. Okay? So this is the construction of this transfer function. Okay? So I repeated this part. Okay? So after this, I copied, after this part, this line, I copied this, okay, below this frequency, I use the subtraction rule based on the asymptotic analysis. There is the result of this, okay? Okay, equation of this, okay? Let's use some equation, algebra, do some algebra. So for the frequencies below omega ci, this is the exact equation, but this is the asymptotic analysis. This is valid up to this point, okay? Then we have this expression, this is FM, and this is TI. TI is this one, and this GVD is here. Then we have a bunch of cancellation. This one cancels with this, and this whole denominator cancels with this, okay? Then we have this, right? Then we have this, and this KVD and the KID, we know this for the buck converter. KVD is VS, KID is VS divided by R, VS divided by R. Then this simplifies to this, okay? And this omega ID, we know this, and omega ESR, we know this. Then equation of this is extremely simple. DC gain is this one, R divided by Ri, and this corner frequency is this one, and this is the omega ESR. It goes to here up to this point, but after this, there is this part, okay? So the frequency below this, we are only seeing below this, then this is the correct equation. Okay? Alright? So because we are using the asymptotic analysis, and the impact of modulator gain or power to double pole is clearly seen here. Okay? They cancel here. FM cancel. Okay? Many people claimed the different expression, slightly different expression of the FM prime, but they cancel here. Okay? It generates very small, minor difference in the color loop design. In the voltage design, they completely wiped out. It's gone. Okay? Wipes up. Okay? So claiming the correctness of the FM expression, FM prime expression is pointless and useless and effortless. It's nothing. Okay? I'm not doing that anymore. Okay? I think the Fred-List expression is the best. Okay? And another thing is, because of this, because of the cancellation of this, what happened? The second order dynamics of power stage gone. Okay? In the voltage mode control, loop gain had some peak. Loop gain looks like it shows peaking. Okay? Double pole was here. But in here, in color mode control, there is a second order term here. There is a second order term here. They cancelled. They cancelled in the manner they generate only this -1 slope. Okay? If they have same shape like this, then that will be the horizontal line, right? Because they have different shape, it reduced to this -1 slope, right? So you should understand this, the impact of second order dynamics and the different modulator gains are practically wiped off. Wipe out is a bad word. Okay, wipe off is the correct word. Okay. then the expression of the VCI for the all frequency range. For all frequencies, okay, we know up this point, there's one additional term here, omega CI, okay. This is also part of asymptotic analysis. After the current loop crossover frequency, it follows this one, FM prime GBD, then there should be a pole here. This is 0, this horizontal line, and it becomes pole. So there is additional pole here. So, okay. So this is the very good expression for the entire range of VCI expression. Okay. So benefit of the current loop is apparent here. Okay. First benefit is second order dynamics of power stage low pass filter is disappeared, is erased, okay, and the FM prime expression, okay, we don't have to argue about the correctness of FM prime expressions, they are disappeared, okay. Finally, this structure is much simpler. The case of voltage mode control. Voltage mode control, we have double pole and 2 zeros and 2 poles, okay, and we cancel the ESR 0, something like that, all right, but this is very simple, okay. You have only 3 single corner frequencies, and this one occurs at high frequency, so it really doesn't affect the design of this voltage loop. It doesn't affect the design of a voltage loop, only this one affects the design of a voltage loop. So design of a voltage loop becomes extremely simple, okay. So summary of control to output transfer function of buck converter case. This is a buck converter case. This can be easily extended to other converters. That is the one advantage of using current mode control. Okay, so this one. So this is the expression we derived. Okay, and this is the full details about this. This DC gain is this one. This 0 is this one. And this ESR is this one. And the omega CI is simply current loop crossover frequency. Okay. Easier than voltage mode control, okay? If you understand everything systematically, all right? Simulation result. This is a simulation result of this control to output transfer function with current loop closed, okay? So current loop is closed here, and this is the control voltage, DC value, lamp of size of external lamp, and everything remains same. And this is the transfer function, generate this computational method using time domain analysis. Okay. So this is this one. Okay. So maybe you cannot see the poles and zeros. This is very not easy to figure out where it is a pole, but there is a poles and the phase characteristic remain is the correct one, and this one is this one. Because the corner frequencies are not widely separated as shown here, you don't see these corners, okay, these corners, but the pattern remain the same. So it may be it is something similar to this, okay. All right. Let me explain this. Loop gain shaping. Loop gain shaping means you are shaping the loop gain in the desired form. Okay. So what we are going to do is desired or optimal form, and we will justify this statement later. Okay. Just believe me now. Believe me now. Okay. So loop gain shaping. This is the loop gain. Loop gain is this one. This is control to output transfer function with current loop closed times FBS. This is a loop gain. You don't have FM or something else. Ri, because this guy contains all of them. Okay, we defined the new power stage model, including everything. All right. So only this one is feedback. Only one feedback compensation involved with this loop gain shaping. Okay. So this is the GVCIS. This is the loop gain structure. I claimed this is the best structure. So it has integration structure, and it has one zero, and it has one pole. Okay. This is a given power stage transfer function, for example. Okay. Okay. This is the control to output transfer function, but it can be considered as power stage transfer function, right? And you need this integrator. Why do you need this? For DC regulation. Okay, our prime purpose is to regulate our voltage at fixed value. For that purpose, you should have this integrator. So integrator is coming here, and you have this pole. Pole is needed to cancel this omega ESR. Why is that? You have this -1 slope for wider frequency range. Okay. And you need this 0, okay, because you have integrator here, okay. This is the GVCI, okay. We are not using this, we are just referring to this when constructing this, okay. So initially we have integration, and integration gain will be here. So it is directed to this frequency, and at this point we have this 0, right, this pole, omega ID is pole. So omega ID is here. So slope is -2. Then at the crossover frequency, phase is -180. System becomes marginally stable or unstable. So you need to place 0 here before the crossover frequency to have sizable phase margin. So you need this to increase, to boost the phase before loop gain crossover frequency. Okay, so it goes like that. That this -1 slope is what desired one. Okay, then phase margin will be something similar to the 90 degree. Okay, theoretically, not theoretically, because you have this one, so it will affect something. Okay, so but this will be good phase margin. At high frequency, you have another pole. This one is okay. Okay, it provides one noise attenuation. Okay, this is doing good for you. Right? So you don't have to worry about this. Then you only need this, and this. That is the structure of 2-pole 1-0 compensation. Alright, so 2-pole 1-0 compensation. Right? And this one is hard to observe. Later on, I'll show you the loop gain of this one. But this is, no. Okay, I'll show you that later, okay? Anyway, it looks like one straight line, okay? Because of they are crowded, okay? And this open loop, okay, omega ID is coming here, and omega PC is located at omega ESR intentionally to have cancel, and at this omega CI is loop gain crossover frequency of current loop. It is coming at higher frequency. Okay, so I wrote down here omega PC at omega ESR to cancel the effect of the omega ESR, and omega GC before this one to boost the phase before the loop gain crossover frequency. This comes later than this, okay? But if you take a close look at this is the 1A of looking. This loop gain is just looking in the output. If you look the system inside of that, if this after this, the system could become conditionally stable. That effect is not shown here. Okay, this is the hidden, because we are just looking this system in the outside. The inside dynamics is not shown here. Okay, but if you take a look at the inside dynamics, then if this guy comes after that, the system becomes conditionally stable. To avoid that, this becomes before this one. So omega GC is coming before omega naught to avoid being conditionally stable system and to obtain the sufficiently large phase margin, and KB. Finally, you adjust K to place the crossover frequency of this loop gain. Okay, location of this crossover frequency is also important. So this is the guideline. Omega CR can be placed at omega ESR. If possible, this is the best place. Okay, but if not, then a bit lower than this one. So 0.3 to 1.0 ESR is the range. Relatively wide range. It depends on the value of your ESR. If ESR is large, you can go this direction. Otherwise, you can go this direction, and somewhere in between is okay. Okay, and selecting this can be done in the trial and error method. Okay, if you increase or decrease this, the phase margin will be changed. Only phase margin will be changed. You can check that from the simulation. Then you can adjust this one. Okay. Then loop gain crossover frequency is here. Okay, this is the far less than this. At this one is less than half the switching frequency, right? Because of the many reasons I already explained, and I more explain about that. Very important. Okay, then that means this omega CR is significantly larger than omega C. Omega C is loop gain of voltage mode control, and omega CR is loop gain of current mode control. Okay, but you can assume this voltage mode control is better than current mode control because of this. That is not true. Absolutely not true. Okay, that never means that this voltage mode control outperforms the current mode control. That is not true. Okay, if you have two systems, just simply comparing this frequency, one is better than the other. It is very dangerous statement. So you should know all the details about this internal, including the internal dynamics. Okay, so this is very important, and I'll repeat this over and over again. Okay, this is so important. Right? Usually this is much smaller than voltage mode control. That does not mean the current mode control is worse than voltage mode control. That is absolutely not true. Okay? All right. Next slide. This slide shows the schematic diagram of current mode controlled buck converter. This is the power stage, and this is the PWM block, and this is the current compensation circuit, current feedback circuit. Okay. First, assume this is connected. Disconnected. Then we can define this Ti. Ti is product of three terms. First one is D hat in the denominator, I hat in the numerator. This is the due ratio to inductor current transfer function, and Ri is current sensing network gain, Ri, and this one is PWM modulator. So FM prime is modulator gain of current mode control, and this term is called current loop, not current loop gain. Okay, I'll explain the reason why. Current loop, not current loop gain. Okay, so in this case, we assume that this is connected to the DC voltage, constant voltage. So this loop is disconnected, right? There is another loop. This is the current loop Ti. There is another loop as defined. This path. We call it TV. For this, we are assuming this is connected, and this is disconnected. Okay. Then this is the TV, and this is also term product of three gain blocks. First one is VO hat divided by D hat is duty ratio to output transfer function, and in the middle we have FVS. Okay, so this is the FVS called voltage feedback compensation or transfer function of voltage feedback circuit, and here we have modulator gain here. Okay, so this is called current loop, voltage loop. Okay, so this is my definition, and I consistently used this all my papers in my book and any other materials, educational materials, any other publication. So the reason I'm using current loop, voltage loop, not current loop gain and voltage loop gain, is because the loop gain is something else. Okay, this is simply gain product of feedback loop. No, not feedback loop. Signal loop. Okay, and this is also the simply gain product of this loop. Okay, maybe you call it transfer function of the loop gain, or transfer function of the current loop, transfer function of the voltage loop. Okay, when you are talking about this is disconnected. When you are talking about this is disconnected. Okay, that is just the current loop and the voltage loop. When you are talking about loop gain, okay, everything is closed. This is closed, and you open the here, and you insert some signal that goes around here, and part of that signal goes around here. That is called the loop gain. Okay, loop gain is used to evaluate the stability of the system, but this individual loop is different. Okay, so some people they use current loop gain and the voltage loop gain and the loop gain. Maybe they are inferring the system loop gain. That is very confusing. Okay, so long time ago, I was thinking about this, and I decided this is just the current loop, voltage loop. Okay, gain product of the current loop, gain product of the current voltage loop, or current loop transfer function and the voltage loop transfer function. Okay, so don't mix current loop and the current loop gain. Voltage loop and the voltage loop gain, they are different. Okay, they are different. For me, they are different. Two different things. Okay, I'll explain that further later. Okay, with a special example. And we discussed this current loop design and this voltage loop design. That is determining this, and that is determining this, and this. And the current loop design is just selecting the slope of compensation lamp. Okay, and the voltage loop design is determining structure of this and evaluating this value to have desired transfer function. Two-pole 1-0 circuit. So this is called voltage compensation, and in particular this is two-pole 1-0 circuit. Okay, so previously we discussed why we need this structure. Okay, and the location of this, that kind of thing was already discussed. All right, so now we are taking a look at this. Right, so this is the feedback circuit. You are using this one. Okay, let me take this out. So this is two-pole 1-0 compensation circuit, and we have 6 parameters. 5 parameters, 6 parameters. This is reference voltage. This can be infinite. That means this can be opened. And this is one resistor. There is one resistor, and this is a parallel combination of the C3 and C2 in series to R2 parallel combination of them. Okay, this let's call this G2 and G1. Okay, and this is the desired transfer function. So initially it has integration. So we have one pole in the origin, and it has 0, and it has pole. So this is the 2 pole 1 0 scheme. Okay. Purpose of using this is twofold. First one is we need to have output regulation. So let's talk about the output regulation first. And later, circuit component, value of the circuit component or circuit equations. Okay. Right? So this is the ideal operational amp. We assume this is ideal. Then voltage here and voltage there, they are same. Okay. So potential of here is V reference. This is V reference. Okay. Then this output. So there is no current coming in. Then this voltage division, this R1 plus R2 in the denominator, Rx in the denominator, and R2 Rx in numerator is voltage division. So this voltage division should be same as this one. Okay. Now we are talking about the DC. So this is VO. Okay. That should be the V reference. Then you rearrange this equation. Then in the steady state, this must be true. Okay. So if R1, Rx, they are same, voltage gain is 2. Okay. If this is the infinity, VO voltage gain is 1. Okay. This voltage division ratio is 1. That output should be the same as V reference. Okay. So this voltage is always larger than or equal to this reference voltage. Okay. So for this, we need to have this. I told you this so many times. No. Evaluate at DC. So this one is evaluate at DC. Put 0 here. Ratio of this impedance magnitude should be infinity. Then always you have this. Okay. So this is the one purpose of this circuit, this part. And the other one is this is the desired structure of voltage feedback circuit. So one pole at origin, another pole at omega PC, and the gain, integrated gain, and 1 0 at omega GC. Okay. If you go back to this lecture in YouTube channel, topic 04, lecture 5, I explained all the details about this. Suppose you have desired transfer function to implement, then how to determine this structure. Okay? Something similar to this, or even more complicated, or even arbitrary transfer function. Okay? And if you have this, directly writing down this, okay, that procedure is very fundamental and easy to understand and extremely easy to memorize. Okay? So let me repeat that first. First, think about this. This is the DC current is coming in through this. DC current is coming in. Then this current goes here, and it divide, I don't know, ratio, maybe together. They sum of them because equal. Okay, because DC current is coming in, then this current should pass through this. Okay, because this is the infinity, this is the infinity. That means this capacitor is charging and it goes this direction. This determines this kV. Okay, kV is determined by this constant. This is R1, and impedance of this is infinity, this is nothing compared to this, then integrator gain, this gain, KB is determined by time constant R1, and this is parallel combination C2 plus C3. Okay? And with these two components, which are this and this, generate zero. So that zero is shown here, and previously it was this KB expression. Okay, zero is here, and finally combination of this and this in this path, okay, closed path. So we have R2 and C2, C3, they are in series. Then formulation of the evaluating the series connection of C2 and C3 is this one. This is not a parallel combination. This is a series combination that determines this omega PC. Okay, so this is this one, right? If you have some other terms, then you can add something here. So by adding this branch or adding one something else here, you can suppose you have this. You have there is additional C and additional R like this. Then you are creating 1 pole and 1 0 here. Okay, so the formula remains the same. That is very simple. If you think about the impedance of this C and R circuit, and I explained we are using only C and R, you can use R and then L, but L is inconvenient to use, but C is very convenient, so we are using this all the time. Okay, don't try to calculate G2 divided by G1. Okay, don't do that. Okay, this is the way of doing this. Right, we have this. Okay, and this is the very simple demonstration of PSIM simulation of this. This is the compensation value we are using, parameter values we are using. So this will generate 2 pole 1 0 compensation. So this is origin. This is the integrator and 1 0 and 1 pole here. Okay. So because the corner frequencies are crowded, you are seeing something like this. Something like this, okay? But this is the asymptotic plot, and this is the real Bode plot, okay? And you need this, right? Because this will generate minus sign here. This is the inverting configuration. So to cancel this inverting function, we add this. This is just sign inversion part. Sign inversion. Okay, and I plot magnitude here. I plot the phase here. But because I have this, so I use this minus 180 degree phase delay. So this phase is okay. Phase start about 90 degree and try to reach the 0, and the final phase is also minus 90 degree. That makes sense. Okay. Okay. All right. So this is the end of this lecture, lecture number 4. But before leaving this lecture number 4, I have 2 more slides. I want to clarify something. You don't have this. I prepared this morning. It will come up in the OCW site. Okay. But this is very simple. All right. In the earlier part of this lecture, we evaluate this. Okay, this is the simulation setup to simulate this PWM waveforms. For that time, this V cone is fixed at this value 3.91. Okay, that value is determined by this. This is the peak value of sensed switch current. So PWM function is something like this, okay? So this is sensed switch current, and this is external lamp, then this should be the control voltage here. Control voltage here, okay? This value is evaluating by this times this current sensing network gain will provide this, and this is the duty ratio times this maximum value of the lamp, compensation lamp will provide this. So these lengths are the same, and you evaluate this, then this value becomes 3.91, okay? If put 3.91 and you put this VRAM, peak value of the VRAM as 2.92, then duty ratio becomes 0.5 and 1/4, and our voltage becomes 4. Okay, so this is the based on that scenario. So D was 1/4 because this is 16 and our voltage is 4. Then D should be this. Okay, we know this value. Okay, we know this value. Last time we evaluate this in the beginning of this lecture, we calculate this, or previous lecture, I don't remember, but somehow when I was explaining this circuit diagram, this is the setup to measure the control to output transfer function with current loop closed. This concept is very important. All right. So concept here is, this is, forget about this part. Without this is the complete, the current mode controlled buck converter with connection here to there, and with connection here and there. Okay, and you disconnect this, and you inserted this circuit to measure this transfer function experimentally or computationally. Okay, so you disconnect this, but you have this condition. To generate these waveforms, you should provide this fixed voltage here. So this DC value is 3.95. We previously calculated in the upper part of this. All right. Then the way doing this is, okay, this is a 0 initially. Then you add some voltage here, maybe 5 volt. This is R, and you adjust this and make this thing 3.19, and this is the unit gain buffer. Then this DC voltage is this one. Okay. Last time I got confused. Okay, I was saying something stupid. 1/4, that is not true. Okay, that is not true. And you put this number here, then D becomes 1/4, and the output becomes 4 volt. Okay, because of the previous analysis. Okay, so this is, then you define this. In this situation, it is this AC path is cut, and you define this TI here. Then TI is this one. We previously went through this, and we call it current loop or current loop transfer function of current loop. We never call it current loop gain. Okay. Okay, think about this. Now, this is connected. No, this is disconnected. This current feedback is disconnected. Okay, and you connected here. And this is okay. This one is okay. Assume this is disconnected. Okay, then there is one loop here. This and this is the one loop. Okay, that can be called voltage loop. So voltage loop is this one. This is your duty ratio to output transfer function, and output to control transfer function. This is what? This is this voltage feedback compensation, and this one is, last one is the modulator gain FM prime. This is called voltage loop. Okay, voltage loop. So current loop, voltage loop. You have two loops, but they are entirely different loop gain. Okay, let's think about loop gain. Then you should connect everything. This is connected, and this is also connected, and this is also connected, and somehow you break this point, okay? You know how to break this, and how to measure loop gain. That was covered in previous lecture, okay, in YouTube channel. Then you can define this as TMS. That is the loop gain. Okay, TMS is transfer function from here to there with this one closed. Okay, then think about the Mason's gain rule, and this transfer function is the fourth gain, which is this. This is the TV. TV is coming here, and in the denominator, Mason's gain rule. Okay, 1 plus Ti. If there is a loop untouched at this point, the loop is coming here. Okay, 1 plus Ti is here. This is the loop gain. This is the loop gain. You can evaluate the stability of this converter using this loop gain, not this one, neither this one nor this one. So entirely different. Okay, loop gain is more than simply gain, product of the loop. That is not loop gain. Okay, this is the loop gain. Actually, there maybe you may call it system loop gain, and there many system loop gain can be defined here. One is here, another one is here, another one is here. Okay, with everything closed, right? But this one is more convenient, and this one structure-wise, this one is similar to the simple loop gain for single feedback system, which is voltage feedback control. Okay, so that's the reason why I select this notation as the loop gain. Okay, so this is the loop gain. It is different from the current loop or voltage loop. Okay, and if converter is voltage mode control, then Ti is 0. Okay, for let me write this down. For voltage mode control, Ti is 0. So maybe we use Tm prime as TV. Okay. In the voltage mode control, we are only dealing with this TV. At that time, TV becomes loop gain. Okay. Voltage loop gain, they're same thing. Okay. In the voltage mode control, but in current mode control, the situation is different. Okay. So this is the one thing. This is the second thing. And another one is, the third one is here. So Tm, based on the Mason's gain rule, is given by TV divided by 1 plus Ti. Okay. TV is Fm prime GVD times FVS. All right. So this is the TV. This times this and this. Okay. And Ti is 1 plus GID RI FM times. Okay. This was what? This is GVCI. Okay. So this part is GVCIS FVS. This is a loop gain, right? Because this GVC is control to output transfer function with current loop closed. So this is a loop gain. This is a loop gain for the voltage mode control case. This is a loop gain for the current mode control. This is a loop gain for the current mode control. This is the current loop. This is voltage loop and the voltage loop gain for the voltage mode control. Okay, current loop is different. Current mode control is different. So clear distinction between this simple loop and the loop gain should be made. Okay, otherwise you got confused. Okay, many people they mix these terms. Okay, they use these terms arbitrarily. Right, that is very confusing. Right. Okay, so this is the end of lecture 4. Okay, in this lecture we investigate Ti, and we investigated this GBCI, and we investigate this loop gain, And we identify the structure of this optimum GVS, and it was found this circuit, 2-pole 1-0 circuit. Okay. All right. In the last lecture, I provided one example, complete example to design the column mode controlled converter and evaluate its performance in comparison with the case of previous voltage mode control. Okay.